Okay, my clock is showing 2:15 now, so let's go ahead and get started with our second and final press conference of the day. It is Tuesday, January 10th at 2:15 p.m. here in Seattle, Washington at the 241st meeting of the American Astronomical Society. I am Kerry Hensley. I'm the AAS Deputy Press Officer. I'm joined today by AAS Media Fellow Ben Cassas, helping up here in the front, as well as our Astrobytes Media intern, Zili Shen. I'd like to invite you to silence your cell phone if you have the ringer on for some reason, or anything else that might make noise during the press conference. There will be several press releases associated with this afternoon's presentations, and those will be going out via our Twitter channel, as well as in the Slack channel associated with the press conferences. The previous day's webcasts have been uploaded to the press kit, along with the links to the press releases and most of the presentation files. So how this is going to go is I'm going to give a brief introduction of each of our speakers, then we'll hear from them in order, not pausing for Q&A in between the presentations, and we'll have Q&A for all our speakers together at the end. For our offsite journalists joining via Zoom, please remember to use the Q&A feature on Zoom to queue up your questions. So the topic of this afternoon's press conference is stars and their activity, and we're going to have 5 presentations that explore different aspects of that concept. Our first presenter, Dino from Northwestern University, will speak on the discovery of the shortest period ultracool dwarf binary. Next, Kniezewski from the United States Naval Academy will speak on building out the census of faint and ultra-faint satellites of Milky Way mass galaxies. Next, Marina Kounkel from Vanderbilt University will tell us how we measure the ages of stars through their angular momentum. Next, Tzanidakis from University of Washington will tell us about the discovery of the deepest and longest known blinking giant star. And finally, Lyra from the Ohio State University will speak on starspots and magnetism, testing the activity paradigm in the Pleiades and Messier 67 star clusters. All right, so with that, I'm going to turn things over to our first speaker and get things underway.
Hi, everyone. My name is Dino from Northwestern University, Sierra. I'm a postdoc there. And today I'm going to present the discovery of the shortest period ultracool binary. So first, what are ultracool dwarfs? These are low mass members of our galaxy and our neighbors. They're 10 times smaller to our sun. And this is the artistic illustration shown below. And they have the size roughly the same as a Jupiter. They have different flavors from M's, L, and T. And they are common members and our friends. And next, I want to talk about the binaries as a concept. These are a common phenomena in observations, and especially short period binaries or closed binaries. They are very useful in calibrating our theoretical models. And as I'm going to show in the video below, this is a binary system. They are eclipsing or going in front of each other. When the light goes from the primary to the secondary, the light gets dimmer as a light curve. And we'll use it to measure the mass and radius. And actually, for this type of stars, the frequency of these closed binaries becomes rare and rare to a very low mass end. And there's actually only 3 short period binaries that are currently known. And shown below is the shortest period one currently known in this field, which has a period of 2.8 days. And the light curves in the left and middle is a primary and secondaries. In the right is another physical parameters I'm going to introduce called the radial velocity. These are Doppler shift of the primary and secondary. As they move away from each other, their velocity changes over time. And can see their orbital phases changes in the blue and red curves. And here, I use KEC, which is the largest telescope in the world, and using the nearest back high resolution spectrometer on that. I targeted a source called M9 dwarf LP413-53. And we found a significant radial velocity variation over just 2 hours observations. And this is a spectrum which requires precise radial velocity measurements. And this it actually anchors this orbital motion of the primary and secondary. As you can see, the source kind of split over time due to radial motion. This is only in 2 hours, and this frame is only 5 minutes in apart, which means you are seeing the star dancing in only 2 hours, which is a live show. And this is observations last month. And indeed, we can anchor its radial velocity curve and its orbital parameters pretty precisely, even though we only cover a quarter of its orbital phase. We had 4 nights of last year. We anchor the orbital period of 0.85 days or 20.5 hours. This is 3 times smaller than the previous current known ultracool closed binary system. And the uncertainty of this measurements is actually less than a second. And let's discuss in the context. This separation is actually as close as the Jupiter and its satellites. And another comparison would be the TRAPPIST-1, which is the same flavor of its type, and it is the most famous ultracool dwarf binary, exoplanet host that hosts 7 Earth-sized planets. And indeed, if you have this binary and this such a close separation, it's unlikely to be habitable or host any other exoplanets. And you might ask, how did they evolve into its current configuration? Indeed, when the star formed, they are fluffier, and we don't think it's going to be in that location start from the beginning, because they will have stronger interactions and move into the closer configuration. Instead, we believe there's actually 2 possible scenarios. The first one is when they start in the outer orbit as a binary, and then they move into the closer orbit over time and stay with the current configuration. Another possibility is that there's a 3-body interaction. Start from the beginning, there's 3 sources, and later on, there's an ejection of the 3rd tertiary component. And later on, the 2 remaining sources become closer, moving to the its current configuration. But future observations are needed to anchor its true origin. And finally, I want to state the key results. LP413-BP3AB is the shortest period ultracool binary system currently known, with a period of 20.5 hours or 0.85 days. Its tight separations likely prevented its formation of habitable exoplanets. It may have formed by orbital evolution or by scattering out a 3rd tertiary star. Finally, we haven't made eclipse measurements, but we have collaborators actively working on this. So please stay tuned. Thank you.
On like hold the spiral. Oh, okay. We can do something about that. I'm also going to get rid of this message here. Thank you.
Good afternoon, everyone. My name is Kerry Census, and I'm an undergraduate at the United States Naval Academy. And today I'll be talking to you about how it could actually rain on the sun and the statistics behind that in a paper that was recently published in the Astrophysics Journal alongside Emily Mason. So how does it rain on the sun? Magnetic field lines undergo magnetic reconnection, which causes a very explosive and highly energetic event called a solar flare. That causes the surrounding plasma to heat up and become less dense. So that travels up the magnetic field lines and then cools and falls back down to the photosphere in this beautiful eye-catching event that you see here on the right from the NASA Solar Dynamics Observatory. And rain is considered to be highly common, but post-flare rain has never had any statistics done in literature. So that's the problem that we wanted to solve. And how we did that is we queried for flares in between 2011 and 2019, which covered the majority of solar cycle 24. We examined all the X-class solar flares. Those are the strongest categorized flares by GOES class. And there's not many of them that happen in a solar cycle. So we looked at all of them. And then we took an even spread of the M-class flares, which are medium strength, and C-class, which are slightly weaker. And we observationally looked at all of these flares. We first noted if this flare hosted post-flare rain, and we also recorded the duration of that rain if it did. And these are the results of that. We compared it across different flare classes. And overall, the main results are that X and M classes do, for the most part, host rain, which is what has been considered to be true all along in science. It's just never been recorded in literature. However, there is a steep fall off around the C-class flares. And this points that there is a direct energy correlation between the flare and the duration of rain you see. So this was the main reason why we did this paper, was to put it in literature, to put the statistics in literature. And we also found that the duration in which the rain lasts for is a direct correlation to the energy of the flare. But as everyone in this room knows and on Zoom knows, that the reason why we keep doing science is because we always discover new things, and that some things come up that we didn't originally intend to find, but it ends up being something beautiful, and that's why we keep staying in this career field. And there are several occasions like that in this paper, which made it a truly remarkable paper to be a part of in a long-term study. But I'm going to share one of the most notable things with you today, and that's that post-flare rain could actually be a predictor for solar cycle activity. And what the solar cycle is, it's really at the root that the sun is like a bar magnet. So you have two poles, north and south, but the sun is also a ball of plasma, and it rotates just like the Earth does. So what happens is those magnetic field lines get drugged, and then they coil up and turn into knots, and that's what are sunspots that we are able to study on the sun today. So we decided to plot the percentages per year, per class of flare, against the annual sunspot number for solar cycle 24. And what we found is that X and M class flares actually do track really well with the solar cycle. And why is this important? Because it's not just important to me and you as scientists, but it's important to everyone. Because if we can predict in the future just how strong the solar cycle might be, that just shows how strong the solar activity could be. And even if we get a general glimpse into what the solar cycle might turn into, it just allows scientists and people around the world to just know what we could expect as we grow into a society that's more dependent on technology, satellites, and GPS use more than ever before. And this result also shows just how quickly we'll reach solar minimum after solar maximum. So the overall implications of this study. Post-flare rain is common. That's what we always thought, but we were able to put statistics to that. And also what we found is that post-flare rain is significantly reduced in C-class flares. X and M class flares could be a useful tracker of the solar cycle, which, as I stated before, is of growing importance because as we become more technologically reliable, we are at more risk of losing our different systems as the sun increases in its activity. Post-flare rain duration could act as a proxy for flare energy release. This is just the simple fact that it's a direct proportional relationship between the energy of the flare, so the strength of the flare, and the duration of rain you see. As the duration goes up, you would expect it to be a stronger flare. So the duration of the flare acts as a proxy to know just how strong that flare was. And another key finding of this study that helps our statistics be even more refined, and we are much more confident in these results because of this, is that post-flare arcades persist for days. Post-flare rain is not the only type of rain that happened on the sun, but what we discovered is that these post-flare arcades persist because it shifts to a different mechanism of heating, and then they are no longer heated by the flare. They can be heated by active region heating, for example, because most flares do happen in an active region. So they transition to a different type of rain, and it's no longer considered to be heating from the flare. So that allowed us to choose a cutoff point from when we should stop the clock of calculating that duration of the rain. So the summary, the paper was recently published in the Astrophysical Journal Letters, and I highly encourage you to look at our other sub-results and unplanned results that came about from this study, because I only hit the surface of what we were able to put in this paper. And overall, there is a correlation between flare energy and rain duration. That was the main point of us doing this study, and we did put that in writing. We do plan to extend our post-flare rain analysis to future solar cycles, so that we can better refine our prediction techniques and have more data to go off of to show that post-flare rain can really be a way to predict how strong a solar cycle might be and how much solar activity we could expect in the future. And that's my contact information. Please feel free to reach out to me at any time if you have any further questions or want any more information on this work. Thank you.
Hello, my name is Marina Kounkel. I am a postdoc at Vanderbilt University, and today I want to talk to you about stellar ages. Chances are, if you were to pick a random star in the sky, you wouldn't know how old it is. Stars have very long lifetimes. Some of them are as old as our galaxy with an age of over 13 billion years, and some of them have only recently been formed. But knowing stellar ages is extremely important because it allows us to understand not only how the stars themselves form and evolve, but also how the galaxy evolves as well. One of the most reliable way of measuring stellar ages is if the star is associated with a cluster with which it has been born. Within a cluster, you have stars of different masses. Some of them are low mass, some of them are high mass, but all of them have exactly the same age because they've all formed at the same time. And as stars of different masses evolve at different rates, by correlating their evolution, we can estimate what is the age of the cluster as a whole. So here you can see the relationship between the mass of the stars versus the brightness. The low mass stars that are young tend to be fairly bright because they are still very, very puffy, but eventually they will settle onto the main sequence. And then after a while, the high mass stars begin to die off because they have very short lifetimes. So through this, we can estimate the age of the cluster, and as a result, all the stars that are associated with the cluster. And this is all very nice because recently there was a survey conducted by Gaia Telescope, which provided us with distances and velocities of stars across the entire sky, which enabled us to identify thousands and thousands of new clusters. And through these clusters, we were able to estimate ages of approximately 1 million stars, which may sound fairly impressive, but there are billions of stars in the sky. Some stars are very eager to leave their nests. And statistically, if you have a star that is over 100 million years, you wouldn't be able to trace it back to its parent cluster. So in order for us to be able to measure ages of stars, we need to have a different method than just the isochron fitting. And one of the ways that we can turn to is by examining spots on the stellar surface. As the star is rotating around its axis, because the spots are slightly darker than the surface of the star, the brightness of the star is going to change ever so slightly. So when a spot is pointing away from us, the star is going to be brighter. When the spot is pointed towards us, the star is going to be darker. And by observing the amplitude of this variability, we can estimate the sizes of the spots. And by looking at the period, we can measure rotational periods. And using Transiting Exoplanet Survey Satellite, or TESS for short, this instrument takes observations of the sky, measuring brightnesses of the stars over a long period of time. And so here's an example of just one of the hemispheres that TESS has observed. And using TESS, we have constructed light curves of approximately 100,000 stars, ages of which we have known, to examine how exactly their variability evolves over time. And here we can actually see the magnetic history of all of these stars, because we see that stars that are very young, that are also fairly low mass, tend to be very magnetically active. They have a lot of spots on their surface. And the low mass stars remain spotted throughout their lifetimes. But higher mass stars and older stars tend to decrease their magnetic activity. For example, our sun has a temperature of approximately 6,700 Kelvin, and it is fairly evolved, so it has fairly wimpy spots. But the young low mass stars can have spot coverage in excess of 70% of their surface. Also, because we are able to measure rotational periods of these stars, and if we are able to estimate masses and radii of the stars, we are able to estimate angular momentum with which these stars are rotating. And as you can see, there's a strong correlation of angular momentum as a function of age. Young stars spin fairly fast, but as they evolve, they begin to spin down. They lose angular momentum over time. So using this diagram, if we know angular momentum and if we know the temperature of the star, we would be able to infer their age. So what we have done is we created a theoretical gyrochrone, empirical gyrochrone grid rather, that would enable to measure ages of the stars in the future. Of course, we still need to measure rotational periods of many, many more stars in the sky using tests that should hopefully happen in the next couple of years. But through this technique, we should be able to significantly increase the number of stars for which we are able to measure ages. Thank you.
Alrighty, good afternoon, everybody. My name is Tzanidakis. I'm a PhD student at the University of Washington. And today it is my great pleasure to announce the discovery of a very unusual and remarkable star that we have discovered, named as Gaia 17 BPP. Now let's get straight into it. This star was discovered through the European Space Agency Gaia spacecraft. Occasionally Gaia will report the brightnesses of objects that change in the night sky. And Gaia also measures the position and brightnesses of billions of stars in the Milky Way galaxy. And so while we were investigating this data set, the Gaia Photometric Science Alerts, we came across a very unusual star. So this is Gaia 17 BPP. And here you could see the optical light curve that Gaia saw. And so you could basically see that the star over the span of between 2014 and 2015 was basically at the detection threshold of Gaia. And then over the years, about 3 years or so, the star began to rise extremely slowly. Now, let me tell you that stars typically do not do this. So when we first saw this, this was really remarkable what we saw. And you could see here in this animation that the star, this was images taken from the Atlas project. And you can see the star was basically invincible. And over the years, the star slowly started to reemerge from the images. So looking through the data archives, we were able to recollect all of the data that we could find about this star. And we were able to go as back until the 1950s using a project from the Digital Access to a Sky Century at Harvard. So these are photographic plates that have been digitized, and then we can use them to make digital detections of stars. And what's remarkable is that you could still see the star here on the top left of the star being in those images. And if you were able to track the brightness of the star over those times, you could see it's essentially flat. And then around 2013, the star suddenly began to disappear. So this is a 72-year-long mosaic light curve that you could see here. And we're able to confirm the dimming event using multiple telescopes around the world, and also some survey telescopes as well. So something that we could say definitely about the system is the primary star. So using both the broadband photometry and spectroscopic follow-up that we're able to conduct at the Apache Point Observatory, we're able to constrain some of the physical parameters of the star. And based off of our modeling, we're able to conclude that this is a cool M giant type star, about 55 times the radius of our own sun, and about 1.2 solar masses. And the age comes out to about 8 billion years old or so. So this is a fairly evolved star. Now, as I said, stars typically do not do this. So our current leading hypothesis is that there's a massive disk that is eclipsing the star as we saw it. And we have some preliminary evidence to suggest this, especially when we look at the color evolution of the light curve using multiple telescopes. And so in this figure here, you could see some of the colors that are basically a proxy for temperature. And so when we take the optical and infrared colors, the star kind of cools. And then in the infrared, when we look at the infrared alone, we actually see that there's a slight bump. This is the top panel. There's a slight bump in blue light, which is possibly indicative of a hot companion at the center of this disk, or it could be due to scattering light from the dust. It's still ongoing work that we're trying to figure out. Now, what's even more remarkable is that if we were to make the assumption that this system is gravitationally bound to the main star, you can make some assumptions based off of the orbit. Take, for example, the radius and mass and duration of the event. This would give us approximately a limit to between 100 days and 100 years and 1,000 years in orbital period. And so what this really is pointing to is that these eclipses are possibly once in a lifetime. We possibly might never see this eclipse again because it takes such a long time. And some of the preliminary modeling already suggests that the size of the disk might be something between 1 and 3 astronomical units and is extremely far away from the primary star. So that's why it takes a really long time for it to complete one cycle. Now, I want to argue that this is part of a bigger mystery that's been going around for about 100 years or so. And this is a star known as Epsilon Aurigae, which we've known actually for over 100 years, more like 200 years. And Epsilon Aurigae was a very similar system. It was a giant star that undergoes these massive eclipses that last for 2 years. And it happens every 27 years or so. And even though we have direct evidence that there was something elongated like a disk that's blocking our view from that star, there's still many fascinating questions about the system, such as, for example, how did the disk come to be? What is the disk made out of? And how often do these systems form? These are really important questions that we need to ask in order to understand the evolution of these kinds of stars. And overall, I think this is pointing into the direction of a new emerging population of binary stars. We finally have the data sets and the telescopes to make these kind of discoveries. There's been a few other stars that seem to exhibit similar behavior, although what we found is that the 17 BPP system by far holds the record for the longest event and also the deepest event that we have found in public data archives. And so as more and more of these telescopes will be coming online, it is very important that we are able to catch these events happening in real time. And future telescopes will be able to see this and help us understand their context in binary evolution. So I will leave my slides here. I've also included my contact information, so feel free to contact me. This is ongoing work, so we're hoping to publish in the next coming months. And I'd like to also acknowledge my advisors, our funding agencies, and all the organizations that have made this research possible. Thank you.
Okay. Hi, everyone. My name is Lyra Tzao, and I am from the Ohio State University Department of Astronomy. I'm a graduate student there, working with Mark Pinsnow. And today I'll be talking to you about starspots and magnetism, how we use open clusters to study activity paradigms. Okay. Sorry, technical difficulties. Okay, so cool stars are covered by spots. The churning convective envelopes on their surfaces generate magnetic dynamos and spots emerge. These spots, for many stars, actually cover a significant fraction of the stellar surface. And these in turn, they block the radiation from the star in their selective regions and force the star to compensate. So stars actually inflate as the result of this process. But the standard models that we use to fit for stars often do not include the effects of stellar magnetism. This discrepancy means that some of the stellar parameters and exoplanetary parameters that we're getting for stars may be inaccurate. But the key to actually linking theoretical models with actual data is in making a whole bunch of these measurements and doing these controlled experiments. So the measurements that we have are limited only to the brightest nearby stars. with existing methods, including the Zeeman effect and stuff like that. So our task was to develop a method which can efficiently give us direct magnetic measurements on stars. And the way that we chose to do it is we use the SDSS collaboration apogee infrared spectra, and we fit for two components in the spectra. So we found the spot that was lurking within the spectrum by separating it out into the ambient surface and the star spot contribution. By doing this, we're able to expand the number of star spot measurements from the star spot magnetism measurements from around 1,000 to 700,000. So we're increasing the samples by 3 orders of magnitude. And what this is doing is this is allowing us to actually look at open clusters, our stellar laboratories in the sky, where stars are formed roughly around the same times and out of roughly the same materials. Now, in this plot, what I'm showing is on the x-axis, this is activity diagnostic. On the y-axis, this is star spot coverage. So low values of activity diagnostic on the left-hand side indicate more rapid rotation. And what you can see is that there's a general trend that occurs in the data where the star spot coverage increases as you go to more rapid rotation. And this is very interesting, but eventually at a certain point it saturates. And this saturation is that we're showing in this work is a genuine saturation in the magnetic field strength and the star spot coverage of the star. This indicates that you can spin the star up even further, but it's not going to increase the coverage of spots on the surface. Now, another really interesting thing is that in open cluster samples, we're able to pinpoint and say every single star within the sample is a true member of the cluster. So we're able to say that if there are appear to be outliers, we can't just simply wave them away anymore. So these stars highlighted to the top right are rotating too slowly to have the activity and the star spot levels that they have, and yet we see them there. So what is going on with these stars? And if there are departures from the mean relationships, what does this do to stellar, to exoplanetary habitability? Because all of a sudden these stars are very active. They drive intense stellar winds. They have strong, high energy environments. And the exoplanet may therefore be impacted by this anomalously high activity. Now, another really interesting thing that has been shown in the literature is that eclipsing binaries have been seen to be slightly overinflated relative to standard models. And what you can see here, this plot is again showing activity diagnostic on the x-axis, so lower values are rapid rotation, and on the y-axis, I'm showing the difference in temperature extracted from our method, which incorporates the effects of star spots, and a method that does not. And what this shows is that when you actually fit two components on the spectra of these stars, you're getting a more accurate temperature for these stars, and you're getting a more accurate radius for the star that reflects the genuine radius inflation that people have observed for some of these stars. So this could affect not only stellar radii, but also exoplanetary radii, because because the stellar radius is often very important in measuring such parameters such as the exoplanetary radius. So around active stars, it is important to actually measure the second temperature component because these stars have modeled surfaces. We've also found in the M67 cluster, which is much older than Pleiades, so this is around the age of our own sun, we see a plethora, this kind of evolutionary schematic of activity as it evolves. So what I'm showing you here is a color magnitude diagram. And down at the lower regions, you can see that this is the main sequence, and I've sized each point by the star spot filling fraction. And so you can see that the star spots are very low for all the old inactive stars in M67. As you approach the subgiant branch, these stars evolve and their convective overturn timescales become longer. So their structures actually become more active. So you can actually see this reflected in the data. And then as these stars expand once again and become giants, they lose their activity once and for all because they are rotating so slowly at that point due to the conservation of angular momentum. So what we're moving towards is the ability to track and measure stellar magnetism and understand evolutionary processes that occur in stars as well. And so as we move to this paradigm of measuring an enormous number of star spots around stars, we're able to actually see whether or not some of our standard ideas in stellar activity are true. These are things such as whether the surface spot and magnetic field strengths really do saturate, which we've shown to be true, whether there are stars that do not fit the traditional paradigm, and what kind of theories could explain these stars, and what effects this might have on the high energy radiation environments around certain exoplanets. We also talk about whether or not actually including the second temperature component in our fits can actually improve our stellar temperatures and our stellar radii, also exoplanetary radii. And then we can also track and understand how activity might evolve over time. So I'm leaving this plot up here, and please contact me if you have any questions. Thank you.
Okay, so now we will get started with our Q&A. Regardless of if you are in the room or watching on Zoom, please get your questions ready and be sure to state your name, affiliation, and who your question is for. And Zilly is going to bring the microphone around to anybody with questions in the room. Let's start here.
Hi, Govert Schilling, freelance from the Netherlands. A question for Kara. You showed there is a correlation between the post-flare rain activity and the current solar activity. But I didn't get how you could use the observations of the rain to predict solar activity. You hinted at the possibility. So how could you use this as a prediction?
Right, so the good question. So the percentages of flares per class per year line up with a nice linear correlation with the sunspot number. So they have the same rate of change over the course of a solar cycle. So that's how we're able to use percentages as a way to predict the future strength of the solar cycle. So it's basically just using a year-to-year relationship and saying, okay, the percentages are increasing by this much per year. So that means that the sunspot number is also increasing that much per year. And then we can then use that as a model to predict how the sunspot number will be at solar maximum. And the sunspot number has always been a classic way to show the how strong a solar cycle is. And that's because sunspots, they form active regions, and the more sunspots there are, the greater amount of solar activity you have. So it is just like a continued cause and effect relationship that the number of sunspots increases the solar activity. So if our percentages are increasing by a higher amount, then that means we would expect more solar activity.
Hi, Adam Mann, freelance. I have a question for Andy. You said that you think these could be an emerging new class of things. Do you think that they all have a similar origin? And do you think that a debris disk, I guess, is explanation for all of them?
Yeah, that's a good question. So based off the literature, we think that at least 3 of these systems are M-type stars, and that's already interesting. The Epsilon Aurigae system, which is the prototypical one, that's an F supergiant star. So the stellar classification itself, I'm not sure if that might be consistent with that class. But there might be also an observational bias that we're seeing here, given that these systems are likely very rare. And so it's still unclear what the connections are between all of these systems. There hasn't been any studies yet that has shown any connections between these systems. However, they all seem to exhibit the same behavior of very long eclipses with a very flat bottom eclipse.
I'm Corey Powell, freelance. Andy, I want to follow up on that question. One thing that came to mind was Boagian star.
Yeah.
And I was wondering, first of all, if these behaviors are, if it seems consistent that these could all be part of the same class, but also just sort of physically, astrophysically, does it make sense you would have this, a giant cloud in a 1,000-year orbit seems astrophysically kind of weird. I'm wondering, like, just in terms of trying to think of this as in a realistic scenario, what do you imagine this might be, or how would you investigate it?
Yeah, so for Boyajian star, the timescales in the variability of the light curve from the Kepler Space Telescope, those are relatively short timescales compared to what we're seeing here. This is on the order of about 7 years or so, the eclipse that lasted. And so the variability itself is a very different of nature. But I do agree that it kind of falls into the class of weird photometric behavior that we're seeing from the stars. I think it's a bit unclear yet if there's any connection with the Boyajian star. The main the default hypothesis here is that there's likely dust that is obscuring the light, and given that the photometric behaviors that we see kind of tell us that this is possible, that it is due to dust, but we need to do more extensive modeling to tell for sure. But I agree with you; it is relatively weird that you would have a cloud that's really far from the star, but at the same time, there have been some models that could suggest alternative scenarios, such as example, white dwarfs that might have debris disks around them and found really far. But exploring those models is still something that has not been done thoroughly yet.
Hi, I'm Shubhajit Karmakar from Monterey Institute for Research in Astronomy from California. My question is, do you have any polarimetry or spectroscopic observation during the deep when, and if you are looking at what feature you want to look, there is any way to confirm that there was actually what theory you are suggesting is happening?
Yeah, so I already alluded to the fact that the eclipse already happened, right? So we already missed it. And this is kind of a message that we need to have more algorithms out there that will be able to catch them sooner. Because once the eclipse happens, we can only rely on the archival data that we have. Based off of our spectroscopic follow-up from the Apache Point Observatory, and this was only done in the optical, we didn't see any other anomalies. I mean, if you were to exclude this dimming event, it looks like a typical M-giant type star. But I agree that polarimetry or any follow-up would have been extremely useful to say a little bit more with more certainty what exactly made the star disappear.
But is it possible that there is a very large spot group, maybe in long-term variation or anything else rather than the cloud? Means how are you sure that this is doing from disk or cloud?
Yeah, so you're asking if the star is able to basically cause the variability itself and not a companion. That's definitely a hypothesis. However, there hasn't been any star that has kind of exhibited that. Maybe one star that comes to mind is Betelgeuse, right? The great dimming event of Betelgeuse, but that only lasted for a couple of months or a year or so. So this is definitely something on the more extreme end. And again, given the limitations of the data, it's kind of hard to conclude definitely.
Hi, I'm Aman Carr from Georgia State University. I had a question for Marina. In your sample, you show how you find age using gyrochronology, using Kepler and TESS. For the older stars, if I'm not wrong, do you or do you not include slow rotators that are low mass? Because Kepler doesn't have that, and as far as I know, TESS doesn't go past 15 days, TESS 10, 15 days. So are you extrapolating for those ages, or is their sample limited to fast rotators?
So our sample only goes up to 1 billion years in age. After that, it may be possible to measure the rotational periods in the future. Unfortunately, right now with TESS, we can't get rotational periods longer than 12 days. With Kepler, it is possible to go to longer periods, but it has a very limited field of view. That's why we use TESS for this analysis. But there will be other surveys in the future. For example, Vera Rubin should hopefully eventually start producing regular light curves. And over time, we should be able to construct light curves for longer periods.
Just to follow up, so with the Kepler long period, are you able to predict what the age would be for low mass using the G-dwarfs or
No,
F stars,
we only go to M dwarfs at the most.
at the most? Okay.
All right, I got a few. One for Lyra. I'd like to know, it's neat that saturation of sunspot coverage occurs at a certain rate of rotation and appears to extend over a very large rate of rotation. But even that small threshold of rotation seems to be much greater than the sun's rate of rotation. If you were to plot the sun on your diagram of stars with star spots and rotation, how much of an outlier is our sun on that diagram? Are we like 80% of stars rotate faster than the sun? Or is it like 99.9% of stars rotate faster than the sun? And how much of an outlier is our low sunspot coverage?
Excellent question. So if you were to plot the sun on that diagram, the sun would be to the right and all the way down. So it's not in the domain that we're kind of probing it in the Pleiades in the plot that I showed. But something really interesting that happens with the sun is something that's called weakened magnetic braking. And this is a process where where for older stars that are kind of sun-like, this is work done by Jen von Saters. We think that eventually that these stars may eventually have some switching process that occurs where the activity kind of declines very rapidly. So.
Okay. Thank you. For Dino, I have a question. You presented multiple scenarios for the formation of these very short period ultracool dwarf binaries. And I'm curious if you're contending that there are unlikely to be shorter period ones or significantly shorter period ones than this shortest one you found, as they would have merged if their envelopes would have overlapped early on.
Yeah, nice question. So the theoretical limit is around 0.2 days. It's possible that we can still see even like a shorter orbital period. So that's actually possible. But because of like a binary fraction actually drops significantly over to a low mass n, so it's also challenging to observe such sources. And also it's actually to a limit of the existing instruments. So I'm using a 10-meter Keck telescope. So maybe if in the future, 30-meter telescope can help us kind of anchor more sources. So that's possible.
Okay, cool. And for Kara, I'd like to know, all of your data seems to have come from one single solar cycle. What advantages do you think you're going to get, or what new lessons might you learn if you can actually start tracking this over multiple solar cycles and not just track sunspot number versus coronal, like not coronal vein versus flare strength, but rather coronal strength versus flare strength over multiple sunspot cycles?
That's a fantastic question. It's been the age-old problem in heliophysics, is that we really only have for many of our telescope systems one solar cycle's worth of data. So solar cycle 24 was the birth of SDO. We have a great observational data from that. But in order to have these predictions be refined, we do need more solar cycles worth of data. So right now we're about 2 years into solar cycle 25. We do have plans to start redoing this analysis, but for the flares of solar cycle 25, and that will be very interesting because 25 has been known to kind of be a slow starter. It's been a very slow solar cycle so far. 2 years into it, you'd think it'd be a little bit heftier, but it's almost like we're still hanging around solar minimum. That would be a great indicator to see how these coronal rain percentages change in this solar cycle and compare that to the maximum in a few years. And then while it is every solar cycle is 11 years, and that takes decades and decades to accumulate data to be able to continually refine this, it is what's necessary to make this a more refined prediction model, because we do only have that one solar cycle so far.
Great. Are there further questions in the room here? If not, I have one for Kara as well. Hi, I'm Kerry Hensley from the AAS. So you talked about these low energy C-class flares that either didn't show the coronal rain, or if they did, it tended to be shorter in duration. So this is probably a naive question, but is it possible that these lower energy flares have kind of like a Seattle style mist or drizzle, and that if you had a more sensitive or like an instrument or one that captured a larger dynamic range, you would actually see more rain in those lower energy flares?
Right. So that's actually not a naive question at all. That is definitely something that is like, we have to put an asterisk marks on where we actually define that low energy cutoff to be with the flares. Because while SDO has some of the best resolution for heliophysics that we've ever seen before, and it has beautiful events, and we can see these rain droplets falling from these post-flare loops, we can't have perfect resolution for everything. The sun is still far away, even though it is close in the field of astrophysics. So we can never have perfect resolution, and that definitely is a thing. So like that beautiful event that I showed on my slideshow, that is like an ideal event on the limb of the sun. It's a relatively strong flare, and you can see into it and see those raindrops falling. But for events that are, say, on disk or off about 40 degrees or whatever, it's very much more difficult to see those rain droplets falling. And especially if they're smaller events like that for C-class flares, it is a lot more difficult to see. It doesn't mean that rain isn't there or that the cutoff isn't where we think it is. It might just have a plus or minus to it. So definitely resolution is a huge factor with that.
Great, thank you for that answer. Do we have any questions online, Ben?
We have one, and again for Clara. This is from Bill Waller of the Galactic Inquirer. He wants to know if there's any relation between post-flare rain and coronal mass ejections.
Okay, so great question. That was another sub-study we did in the paper that I wasn't able to hit on in this talk, but there actually is not that strong of a correlation. There is for X and M class flares, which are the stronger range of flares, but more strong flares are pretty explosive events, and most of them host CMEs anyway. So we can't say that that's a scientific certainty that there is a correlation between post-flare coronal rain and CMEs, or if it's just a statistical relation that we were able to make. And it is perhaps unsurprising if they aren't related, because while flares and CMEs are both related by the process of magnetic reconnection, if that flux rope that would be the CME that would shoot off into space becomes unstable, that doesn't have anything to do with magnetic reconnection at all. So if there isn't a relation, then it isn't that surprising that there would be. But our results did show that there was some correlation for stronger flares, but at the end of the day, we can't say if that's a scientific relation or a statistical phenomenon, since CMEs happen for strong flares.
Great. All right. Are there any last questions from people either online or in the room? All right.
Thank you. A follow-up with Dino. You mentioned there were two known ultracool binary systems. You talked about the value of these systems for calibrating the models of these ultracool dwarfs. I'm wondering, have those two systems been studied enough to produce useful calibrations or adjustments? And what could you learn from this system and kind of build on what we already get from the others?
So let me just make sure your question is like, we have like previous, say, three systems, and they can anchor fundamental parameters, set parameters such as the mass and radii. So
Have they produced useful calibrations or adjustments in the models?
So the mass and radii, so observationally is really inflated compared to theoretical models, but we don't have enough data points yet. And for the system I'm presenting, we don't have the eclipse measurement. And then actually, based on inclination, which is crucial in anchoring if they're eclipsing or not, is actually not highly likely. But we still have to make sure once observations are conducted. So.
Great. Okay. This is probably our last call here for questions. If not, then thank you all so much for joining, and thanks especially to the PIOs who helped to prepare press releases, as well as our sponsor, the University Space Research Association. We will be back here tomorrow in this room at 10:15 a.m. learning about building systems in our local universe. And with that, let's thank our speakers one more time.